Hello. Today we're going to discuss solids, liquids, and gases in terms of what happens with particles in them, what happens with atoms and molecules inside those three states of matter, and how they different. First of all, uh, there are two influences here that we need to discuss. One of them is trying to pull the particles apart, and the other one is trying to pull the particles together. So, what is trying to pull the particles apart is basically heat, is thermal energy. Heat in a macro world is just movement in a micro world. So, if something has a higher temperature, that means that the particles inside of it have more kinetic energy and move more. And it's obvious here that gases are on the highest temperature, right? I mean, we know that from everyday life, and we also can see that from these particle diagrams because the particles will move more kinetic energy, again, more heat. So kinetic energy or temperature is trying to move the particles apart. Now, what is trying to put the particles together or hold them together are intermolecular forces. All of them that we discussed thus far, including the metallic and ionic bonding. So, uh, intermolecular forces or any type of interparticle interaction, I should say, are what's trying to hold uh, matter together, basically. And then it's just a question of which one prevails. Does the kinetic energy, does the heat prevail, in which case you have a higher state of matter, or does the do the interparticle forces basically prevail? Uh, Now, all of these states of matter have movement. It's wrong to think of a solid as particles not moving. Solids still have, as you can also see here, there is movement. You can see this double arrow. What does that mean? So, all states of matter have a vibrational type of movement. You will see as you reach higher levels of chemistry after AP that uh, all particles have vibrational movement, and most of them also have a something called rotational movement. So, even solids, even at very low temperature, they always show some movement. So, in a solid, particles are closely packed together. There are strong forces between them, and they're moving by vibrating and basically bumping into each other. They can't switch places, though. That's something that a liquid could do, but not a solid. But they can just bump into each other and kind of transfer a little bit of kinetic energy very slowly between themselves. Now, you can see here that there are two types of solids, a crystalline and amorphous solid. So a crystalline solid is anything that has an ordered structure. So it's either an ionic lattice or it is an ordered covalent, giant covalent network. While amorphous solids, I mean, that can be like, I don't know, frozen methane, whatever, or wood, or I mean, wood is a mixture, not a pure substance. But let's say there are these two examples that we kind of used. So this on this side, these are basically two types of glass. This is crystalline glass. This is quartz, or I mean, you guys know what is Swarovski crystals, for example. So crystalline glass or quartz is ordered and has a structure like this, while just plain old glass has an unordered structure and it's amorphous. So this is crystalline. This is a crystalline solid. This is an amorphous solid. So once again, anything that has an ordered structure belongs to this, and anything that doesn't belongs to this type. Liquids. So in a liquid, you again have particles closely packed, touching each other, vibrating, moving. But in this time, they have enough kinetic energy. They have more kinetic energy than solids, obviously. They can also sometimes switch places. So particles can actually move more than in a way that enables them to do more than just bump into each other. A liquid just as a solid has a stable volume, so you cannot really compress a liquid. You can actually compress it with just a little bit. But as opposed to solids, liquids don't have a stable shape. So they will take a shape of a container in which you basically just pour them. So the volume is not changeable, but the shape is is changeable. And finally, we've got gases. There will be much more talk of gases when we start talking about ideal gases. So basically, in a gas, particles are mostly free of each other's influence. So kinetic energy mostly is winning here. So, and particles are moving, we say chaotically, randomly. They're moving inside a container. There is an interparticle interaction. So they are influencing each other, but just that influence is really low. It has very small impact. So gases have a lot of space between the particles, so you can squeeze them. So you can take a gas like here. This is gas at low pressure, and this is gas at higher pressure because you put it in a smaller container. And pressure depends with gases, as you will see again later. Pressure depends on how much particles of gas hit the wall of the container. So of course they're going to hit the wall of the container here much more than here, and therefore exert higher pressure. So they can change shape, they can change volume. That is how they're different in macro type observation thing. That's how we differ them from liquids and gases. And here you've got an overview of these uh, properties. So for a solid and liquid, we say particles are in contact, while in a gas we say particles are far apart. This terminology is not that much used, but I mean you can remember it. It's good, and you will encounter it later. So vibration only for solids, for liquids translation, which means switching the two particles, and collision, and for gas just random movement, right? And here you've got shape, volume, and ability to compress. Now let's see some examples, and you don't have this as a separate set of questions in AP. You don't have this chapter there, but you do have a lot of particle diagrams. You will have a lot of this incorporated throughout Unit 3 and Unit 4 also. So you've got three diagrams here. Identify the phase that each represents and give the feature of the diagram that justifies your choice. So this is obviously a gas because there's random movement. I'll choose to justify it like that. This is obviously a solid because there is movement, but this is ordered. You can see this is a crystalline solid. And this is liquid. So the particles are touching each other, they're in contact, but uh, there is there's a disorder, and you can see there's more movement compared to B, right? Okay, this one is interesting. So there are three proposed diagrams of vapor. So you can see right here, this is water, and this is also water. So they say that one of these is correct, the other two are not correct, and it's vapor. So it's a gas. It's a gaseous state. Well, if you take a look at these three, all of them basically are a gaseous state. But it's just a gaseous state of what? If you look at this, you can see here that the oxygen and hydrogen atoms are separated. So when you evaporate water, when you turn water into a gas, you don't separate oxygen and hydrogen. You only cut the bonds between the molecules, but not the covalent bonds in the molecule. We talked about this a lot. So A cannot be correct. Now B and C could both be correct, but these are very strange diagrams. They didn't show me the movement. Now, this one looks more random. However, here this is a weird question, and like questions like this, they will give sometimes in an AP. So you will notice that there are four molecules here and four molecules here, but then there are seven right here. So I would choose this as a correct answer just because of the way the question is worded, because this would mean that the number of particles have increased, which is not really a something that can happen because we're considering the same number of particles here. And yeah, that's actually exactly what they said. So seven molecules are shown for C, and the liquid had four. So they're assuming that one of these, only one of these can have more molecules and the other two cannot, which is a weird way to do it. But I mean, okay. So these are two both random. So I just chose this one because this one has had more molecules, and I assume that's not what they want to do here. Uh, Third question: 1 mole of water occupies about 19.7 milliliters and about 18.8 as liquid. So first we have to address this. See, it says 1 mole of water occupies 19.7 milliliter as ice, but 18.8 as liquid. See, water is special. We need to remember that one more time. We discussed it before. So ice floats on water, which means water is different than most other compounds, because for most compounds, uh, a solid will be more dense compared to a liquid. But for water, a liquid is more dense compared to a solid state of water, which is ice. And that is why ice can float on water. This is not normal. This is not very common in nature. Why that happens is because, oh, not that one. Sorry. What did I do? Yeah, this one. So this is the structure of ice. So water molecules bonded with these are would be hydrogen bonds. And take a look at this. This looks crystalline. This looks very, very ordered. So ice has a crystalline structure that allows molecules to be strongly connected and yet very much spread out. So actually, in ice, the molecules are more spread out than they are in liquid water. That is why, for water, if you turn it from a solid to a liquid, you actually have a slight increase in volume, or you will have a slight increase in density, not a decrease. And at 100 degrees, this is the volume. So you can see it increased a couple of like three orders of magnitude, which is normal because when you turn something from solid or liquid into a gas, when there is so much space between the particles, then of course it will have a much more higher volume, and that's usually a couple of thousand times, at least 1,500 times bigger volume for gases compared to liquids and also solids. So that's your answer. A sealed syringe contains air. An identical syringe contains water. When the plunger is pushed with the same force, the air is easily compressed to a smaller volume, but the water is not. So the question here is basically why we can compress air, but we cannot compress water. Well, I mean, we already answered it, because in water, even though the particles can move, they're still pretty closely packed. So there's no space in between them to compress. While for a gas, there's so much space in between particles that by increasing the pressure from the outside, I mean, that also increases pressure from the inside, you will push them closer together and make the total volume smaller. Steam is cooled until it condenses into liquid water. Using a particulate model, state what changes and what stays the same, and identify what must be overcome or form for the changes to occur. So steam changes into liquid water. I don't like this diagram. These should be a bit closer together. I guess they're just trying to make it look nice. So these should be touching. So the number of water molecules stays the same when you change the state of matter. The spacing changes. So when you compress something into liquid, particles will start touching each other or almost touching each other. What stays the same? The identity of each molecule. So the molecules, again, they don't fall apart. No covalent bonds are broken, and also the number of molecules has to stay the same. Remember the first question. The average kinetic energy changes. Of course, they had a lot of kinetic energy as a gas, and now they have much lower kinetic energy. Covalent bond stays the same. Okay, we already discussed that. So the hydrogen bonding between the molecules actually is higher in a liquid. I mean, we said that to change something from liquid to gas, you have to break most of the intermolecular forces, because in a gas, only a few intermolecular forces remain. And in the ideal gas, none of the intermolecular forces remain. At 25 degrees and 1 atm, methane is a gas while water is a liquid. Why? Well, water has stronger intermolecular forces. So water has hydrogen bonding, has dipole-dipole. But again, as we discussed before, hydrogen bonding is much stronger than everything else. So that means that the water will be a liquid at a temperature of 25 degrees. Why? Because strong intermolecular forces, while it's very easy to make methane into a gas because it only has London dispersion and very weak London dispersion forces at that. The two samples of solids are represented below. Identify which is crystalline and which is amorphous. This is crystalline, right? It's ordered. This is amorphous. It's much less ordered. And it's very easy to identify. For almost every substance, the solid is denser than the liquid, yet ice floats. 1 mole of ice occupies this. Okay, so we explained this before. I just wanted to show you a better picture because this one is not that good. So one more time, ice is very ordered, but it also allows the molecules of water to stay basically spread out, even though they're in a solid state. Wait, check these questions out and let me know if you need any help. Good luck and bye bye.